So, basic refrigeration cycle. Here we have a simple schematic, a basic DX system, direct expansion, and the major components here are the compressor, the condenser, the expansion device, and finally the evaporator. A good way to think about a refrigeration system is there are two distinct halves. So on the discharge side of the compressor, we have the hot side, and on the suction side of the compressor, we have the cold side. Sometimes people refer to this as the high side or the low side. On the left-hand side, we have high pressure or HP. On the right-hand side, we have low pressure, LP. On the left-hand side of the compressor, we have the discharge side, which would be the discharge pressure. And on the right-hand side, we have the suction side, and we would call that the suction pressure. Now we talk about the evaporating and the condensing temperatures. And then we abbreviate this as the saturated condensing temperature or the saturated suction temperature, SST there at the bottom. So here we go with the refrigeration cycle. So basically the compressor's job is to compress the refrigerant gas and create a high pressure gas which is superheated and flows from the discharge side of the compressor from 1 to 2 the condenser. The high pressure superheat vapor has to lose its superheat in the condenser, and then it begins to condense into a liquid. A mixture of liquid and vapor leaves the condenser and moves along the liquid line, which is 3, towards the expansion device, which is 4. When cooling is required, the expansion device opens and high pressure liquid refrigerant changes state from a liquid to a gas in the expansion device. Now, a good explanation of what is happening at the expansion valve is if you picked up a can of aerosol containing lighter fuel and shook it, you can feel that inside there's a mixture of liquid and vapor. Well, actually, what is in there is a liquid which is trying to boil, which is butane, at minus 42 degrees. But it can't expand as it's held under pressure in the aerosol. Now, as you push down the nozzle, the pressure is released, the liquid expands and changes state to a vapor. And actually, I'm sure people have filled up lighters to see that you do create a cooling effect around the bottom of the lighter. So as a refrigerant changes state, it absorbs heat in the evaporator here at 6. And once again, it becomes a low pressure gas and returns to the suction side of the compressor at 7. As suction pressure increases, it will bring the compressor on and will start. And once again, high pressure refrigerant vapor flows from the compressor to the condenser. And the cycle is repeated. Hope that makes sense. Here are some rules of thumb, some just very, very good basic bullet points here. So port installation and design and maintenance can reduce refrigeration efficiency by 50%. Something can be installed incorrectly, but will still work. Now, it may be less efficient and not meet its rated performance. Now, this is an important statement because much of the equipment that gets installed today could be used for the next 20 to 25 years. And in terms of meter rated performance, it's extremely difficult for anybody to tell if the system is not meeting its rated performance. So it could go undiagnosed, unchallenged for 20, 25 years. Now, the compressor motor absorbs 95% of the energy in a refrigeration system. It's by far the biggest user. And condenser fans only account for circa 5 or 10% of the energy consumption refrigeration system uses. Any increase in condensing temperature will affect the efficiency of the compressor. And as I said, that accounts for 90 to 95% of the consumption. So it's really important to understand that the more heat the condenser rejects, the less work the compressors must do. And for each 1 degree increase in condensing temperature or system lift, and we'll talk about system lift later on, refrigeration efficiency reduces by 2 to 4%. And this is without doubt probably the biggest area of energy saving in refrigeration.